So, welcome everyone to this teacher info session where we're going to present firstly a history of Mars from Athanasia Nikolaou Plesa and then the resources developed by Europlanet on the topic of Mars that you can use in your classroom. But first, I want to introduce Ina to all of you. So, Ina received her PhD from the University of Münster in 2014. So she's 10 years a researcher and even more if you count all the time of the PhD. She's a researcher at the DLR Institute of Planetary Research, where since 2019 she leads a junior research group. This group investigates the thermochemical history of Mars and of Venus, but she's active in many other planetary bodies as well. Her research focuses on the evolution and the interior dynamics of terrestrial planets. She combines numerical modeling and planetary mission data together. So she's going to give us an introduction to Mars so that we understand better what we're talking about for this planet. And Ina, the floor is now yours.
Thank you so much, Nadia, for this nice introduction. And yeah, welcome everyone. I'm going to put this in full screen. And as Nadia said, I'm working at the German Aerospace Center. I'm here a senior researcher and looking into the dynamics of planets in general, but of Mars in particular. And today I'm going to talk a bit about Mars, what we know about Mars, what we can use in terms of models and observations to understand what's going on Mars. Right. So first of all, why are we interested in Mars at all? Well, Mars, if you look at our solar system, Mars is, as the Earth, a rocky planet, and it's an Earth-like planet. And as you can see here, Mars orbits the sun, our sun, at the edge of the habitable zone, right? The habitable zone is the zone around the star, is the region around the star where you could have liquid water at the surface of a planet. And we think that Mars has had liquid water in the past. We see this signs of liquid water on the surface of Mars from the past time, and we will see this in more detail in the presentation later on. So it's important to understand Mars because, as I said, it's kind of located at the edge of the habitable zone. And some of the main questions that we have for Mars is like how Mars evolved with time, what was the evolution of the planet, was Mars ever habitable in the past, and what can we learn from Mars for the Earth? And you see here kind of like a sketch showing the earliest stages of planetary evolution, where we have the formation of planets through collisions and through planetary growth. And then this kind of collisions, they input a lot of energy in the interior, leading to a large-scale melting of the interior. So we talk then about a magma ocean that with time crystallizes and sets the stage for the later planetary evolution. And here, these are numerical simulations that we use to kind of like model physical processes that take place in the interior and connect the interior processes that take place in the interior of planets with what we observe at the surface, like this kind of volcanic features that we see today at the surface from planetary emission data. Right, so as I said before, Mars is a rocky planet, and as all the rocky planets contains an iron-rich core, a rocky mantle, and a rocky crust. And just to give you an idea of the size and of the interior of Mars compared to that of the Earth, so basically when we look at Mars in comparison to the Earth, we see that Mars has about half the radius of the Earth, but only a tenth of the mass of the Earth. In terms of the surface temperature, Mars is very cold, minus 63 degrees Celsius on average, compared to mild 15 degrees Celsius that we have on the Earth yearly average. In terms of the density, because Mars is smaller than the Earth, we have a smaller density inside of Mars. And Mars, as the Earth, has an atmosphere, but a very thin one. And we will see this later on the slides. This atmosphere is basically, the atmospheric pressure is very, very low on Mars. And in terms of the magnetic field, we know that on the Earth, we have a magnetic field that is generated in the Earth's core. On Mars, currently, we don't have an active magnetic field, but we see the fingerprints of a past magnetic field on Mars. So we know that Mars at some point had an active magnetic field. And this, of course, is important because it gives us some idea of how the planet evolved with time. Now, when we look at the Mars exploration, this is a sketch from European Space Agency that kind of shows the timeline of Mars missions, starting from the 1960s and going all around until present day and the future. So on Mars, we had about 49 missions. About half of them was successful. And basically, Mars exploration started in 1964 with the first flyby by Mariner 4. And the first successful landing that we had on Mars was in 1975, where the two Viking probes landed on the surface of Mars. And when you talk about the exploration, the general strategy was basically doing the flyby, then going into the orbit around the planet, land on the surface, and eventually return samples back to Earth that can be analyzed in laboratories on the Earth. And basically, over the 5 past decades, we have a wealth of data that we have acquired from orbiter and landed missions. So we have global data sets on Mars where we can actually see the elevation. We have global elevation data on Mars that you can see here on this globe. We have information about the gravity field of the planet, the magnetic field, the crustal remnant magnetization, thermal inertia, albedo, composition, and so on. And all these data sets kind of like give us a piece of the puzzle that we can use to kind of reconstruct the thermal history of the planet and understand the planet as a system. Now, most of the time, the data that we have depends on what kind of instruments or what kind of missions do we have. So we have sub-millimeter scale detailed knowledge at landing sites where we have landed spacecraft. Like, for example, here, this is the Phoenix lander that landed close to the Martian North Pole, or at the location where we had rovers on Mars. And the Mars exploration typically focused on the search for life and on detecting water on Mars. And this is what you can see actually here below. This is kind of like a trench that was dug by the robotic arm of the Phoenix lander, where you see this whitish color here. This is basically ice located in the subsurface that sublimates, that basically goes from the solid form directly into the gas form. And this is because of the atmospheric conditions that we have on Mars. So the ice does not go into liquid form first, but it goes directly from solid to gas form. However, for the interior of the planet, most of the time we don't have direct measurements. So we have to derive our knowledge by indirect methods and models. But this has changed with the arrival of the InSight mission. So InSight mission is a landed mission. It landed close to one of the big volcanic centers on Mars at the border of the dichotomy of this difference in altitude between southern and northern hemisphere of Mars. And the InSight mission brought the first seismometer to the surface of the planet. Well, actually, there was a seismometer on the Viking mission, but it didn't work as expected. At least the data was very noisy. But with the InSight mission, the seismometer was placed at on the surface of Mars and recorded seismic events on Mars. And this kind of like helped us to determine the interior structure, so to accurately understand the interior structure of the planet. And thanks to the data that we have collected with this mission, we know now that the crust of Mars is thinner than was previously thought, using indirect measurements, indirect approaches. And this crust has to contain a lot of heat of the heat budget that the planet acquired when it had formed. Also, what we could say is that the thermal lithosphere is much thicker than that of the Earth. So on Mars, we have a thermal lithosphere of about 400 to 600 kilometers. On Earth, this is typically 100 to 200 kilometers. And also another important piece of information is the size of the Martian core. So thanks to the InSight data, we know that the Martian core is large and it has to contain a significant amount of light elements like sulfur, but also oxygen, carbon, or even hydrogen. And these light elements basically bring the density of the core such that we can explain the density of or the mass of the planet. And these light elements are important because they also have an important property. They decrease the melting temperature or the crystallization temperature of the core. On the Earth, when we talk about the Earth's core, we know that the Earth possesses an inner core, and this is due to the fact that the planet cools and the core starts to crystallize, and it crystallizes an inner core. Now on Mars, because we have this high amount of light elements in the core, the melting temperature or the crystallization temperature is very low, meaning that the core, in order to be able to crystallize an inner core, it should have cooled extremely. And this is something that from models we don't see, meaning that in this case we could say that the core of Mars is most likely entirely liquid. And this again puts constraints on the thermal state of the interior of the planet. Now, let's have a look at the timeline of events. So how we think that Mars evolved with time. So we start about 4.5 billion years ago when the planet started to form by collisions of planetesimals and accreting mass. Now, these violent collisions, of course, also introduced a lot of energy into the forming planet, a lot of heat, and this has led to the formation of a global magma ocean. You have like completely molten silicates, and during this time, the planet starts to form its core. And then with time, this global magma ocean starts to solidify, starts to cool and to solidify. And this leads to the subsequent evolution, to the later evolution of the planet. Now, on Mars, I mentioned before, we know that Mars has had a magnetic field in the past. And this is something that we can actually look at to see when this magnetic field was active. And we do this by looking at the surface of the planet and looking at which regions have been magnetized. So the crust basically records the fingerprint of this magnetic field. This is a timeline of events. Here we have 4.5 billion years ago, and here we have present day. And the axis here is not linear, so it does jump from one timeline to the other. And what we can see here, so first we have this region here, the Borealis Basin, which is kind of shown on this topography map as this area here in the northern hemisphere, which is thought to have formed by a violent collision in the very early history of Mars. So in the very early history of Mars, you had an impact that stripped off parts of the planet, parts of the northern hemisphere, and you have this difference in the north and the south on Mars. And this region here is magnetized. So basically, it kind of like gives us information about an early dynamo. Now, with time, more impacts have occurred on Mars, and these are some of the biggest ones: Hellas, Isidis, and Utopia that you can see here. Hellas is this one, Isidis is this one, Utopia is this one here. And basically, the absence of magnetic fingerprints or magnetization of the crust in these regions tell us that at that point, either the magnetic field was weak or it was absent, or these impacts actually led to erasing the magnetic signature. And then later on, we see again regions that have been magnetized. This is this Lucus Planum here. That is basically one of the regions on Mars, one of the youngest, one of the most recent regions on Mars that have a magnetic signature. So we can use this in order to kind of like provide a timeline of the dynamo on Mars. And this is what we can see today. So this is the crustal magnetization on Mars. And you see here these large impact basins, Hellas, Utopia, Isidis, and also some more volcanic regions that are that don't show a strong magnetic signature, meaning that at the time of their formation, either there was no magnetic field or their formation itself has erased the magnetic field signature. Now, moving on, we in addition to the magnetic field, we also see that we have volcanic activity on Mars during the evolution, and this is important because again, this tells us something about the planet itself. So what we think it happened, this is how we model the interior of Mars and how we kind of connect the processes that happen in the interior with what we see at the surface. So basically how heat is being transported from the deep interior to the surface, how the planet cools with time, and how the planet feeds its volcanic centers that we observe at the surface. And I hope that this video runs relatively smoothly. But in principle, what you see here are these red hotspots, upwellings that transport heat from the very deep interior towards the surface. And this is typically how planets cool with time during their evolution. And you see how these mantle plumes, this is how we call them, these hot upwellings, they kind of locate beneath volcanic centers. And we think that these are basically the feeding regions for volcanic centers. And volcanism is important because it not only shapes the surface of a planet, but also feeds the atmosphere. Right, so volcanic outgassing helps to build up an atmosphere. And we know that on Mars, we must have had more milder conditions, warmer conditions in the past, because we see at the surface, we see traces of liquid water. Now, these are some close-ups of the volcanic centers. Here, this is the Elysium region, and this is this area here. And here we see the Olympus Mons volcano, which is the largest volcano in the solar system, 21 kilometers height, and is located here in the Tarsis area. And these two volcanic regions have been active over most of the thermal history of the planet. We see very young lava flows, a few million years old in these regions that kind of indicate that Mars has been active up to the recent past. So as I mentioned before, we also see traces of liquid water on the surface of Mars. Now, as I mentioned before, also liquid water is not stable today at the surface, but we see that liquid water was stable previously in the past, which kind of gives us an idea that Mars has had more milder conditions at its surface previously. And today, kind of the surface of Mars is looks like this, like we can see it on the map. These are the two volcanic centers, the Tarsis region and the Elysium region. And today, Mars is kind of like a very cold desert. So as I said before, liquid water is not stable at the surface, but we see traces of past liquid water. And these are some of the examples here. We see kind of like outflow channels. We see deltas as the same kind of deltas that we see on the Earth, but without liquid water in them. So they're kind of like traces of past activity, past water activity. Here at the top, you can imagine you have an impact onto the surface, and if you have some ice into the subsurface, you have kind of like this outflow, catastrophic outflow from the impact location. And also we see kind of like the traces of glaciers on the surface of Mars. And as I said before, the surface temperatures are relatively cold, and most importantly, the surface pressure is very low. 6 millibar. On Earth, we have on average like 1 bar. So the surface pressure leads to the fact that when you have ice on the surface of Mars, if you expose ice on the surface of Mars in equatorial regions, this ice tends to go into the gaseous form. It sublimates. So I think my time is over. I'll just leave you with a movie from European Space Agency, from Mars Express. This is a new color mosaic of the planet that has been produced to mark the 20 years of Mars Express operation. And yeah, if you have any questions, I'd be happy to answer them. Thank you.
Thank you, Ina. That's a very nice video, actually. I see it from the Mars Express. So you mentioned actually that we have visited the first time Mars in 1964 and then 75, so every 10 years, kind of, we started. But now we are looking at a mission that is there continuously for the past, I don't know, Mars Express is how many years?
More than 20 years. Last year was the 20 years anniversary of Mars Express.
Okay. Yeah, so I can ask the public, like anyone who would like to make a question, they can simply unmute and ask their question, or write it in the chat as you feel more comfortable. In the meantime, I can ask maybe one question, which is about the desert that you mentioned, like Mars is a cold desert. So what is the highest temperature you can expect during daytime in Mars, in the best conditions?
Well, I think you can go around like a few degrees above zero around the equator. But it's nothing compared to summers that we have on the Earth. Also on Mars, what's important, because we have an atmosphere, but it's very, very thin. You have very strong variations in the day and night temperatures, so much stronger variations than what we have on the Earth. Because on the Earth we have our atmosphere is kind of like buffers the temperature between day and night, so you don't have like strong 20 degrees or more variations between day and night. This is typically for bodies where you don't have an atmosphere, or you have a very thin atmosphere, you have these very, very strong variations.
And the ocean that you mentioned, that we have indications that there was a wet past in on Mars, was again with the same temperatures, more or less, or there was a different climate back then?
So colleagues think that basically in the past we had much warmer conditions, and that Mars might have had a more thicker atmosphere in the past. And typically, the idea is that the magnetic field shields the atmosphere from solar winds, and you have, if you can keep that atmosphere, you can also keep more milder conditions. But of course, as the magnetic field slowly went away, of course, the atmosphere was also more subjected to solar winds and to atmospheric loss processes. So we think that Mars might have had a more thicker atmosphere in the past, but then it lost some of its atmosphere, and that led to the fact that the temperatures changed, the atmospheric condition changed, and also the water that was once at the surface of Mars either was lost to space, or to some extent it trickled down into the subsurface, and it might be locked into the subsurface in form of ice reservoirs.
So that's a good hypothesis for searching for life underground, right? That's
exactly
our main.
Exactly.
Our
Actually,
main...
the underground, people think that the underground is perhaps the most longest lived habitat on Mars, because you are shielded by the harmful radiations. And then if you have warmer temperatures over longer periods of time, you're not subjected to strong temperature variations. And if you have some water in the underground, then this would be kind of like the perfect place to look for life on Mars.
Okay, we have two questions in the meantime. One from Plerton Krasniki, if I say it correctly, who is asking, did the magnetic field of Mars change in the last 20 years like the Earth? If it changed, how much? I guess he refers on the magnetic cycle of the dynamo for Earth for the last 20 years, because that's a variation, right?
Yeah.
So what do we know about it?
So we don't know that much about it, but at least from modeling sides, we do see that Mars might have had magnetic reversals, magnetic pole reversals. Now, of course, the magnetic field is still an open question how long it lasted, because for some time, people have thought, oh, maybe the magnetic field only lasted for 500 million years, because we see that some of the surfaces are magnetized, but others are not. But more recently, there was like this location that I was showing on the one timeline of the magnetic field, where colleagues have looked at that region, and they saw that it is magnetized. And when you date that region, you see that the magnetic field must have lasted until about 3.7 billion years ago, which means the magnetic field was longer there than 500 million years. Whether it was longer than even more towards present day, we don't really know. But this is something that people are still working on, and looking both with modeling but also with observations to see like what regions are magnetized, what regions are not magnetized. And by dating those regions, you can place constraint on the timing of the magnetic field. Now, this pole reversals is difficult to derive them from observations, but we have models. So we can model actually the physical processes that lead to dynamo generation in the core. And in these models, we actually see that it's not uncommon to have these reversals in the magnetic field, the same that we have on the Earth once the magnetic field was active on Mars.
Mm-hmm. But this would be in the past.
Exactly,
It's
exactly.
not
That would
anymore
be, no,
the case.
exactly. Not at present day, but definitely in the past, this could have happened.
Okay. And the second question from Elena Domingo is how we could explain to students of 11 years old that Mars is liquid inside as well as the outer core of our planet, without entering into many details.
So I think there are two things. So first of all, on Earth, we know that we have a liquid core and a solid inner core, so a liquid outer core and a solid inner core. And this is the liquid part because the mantle itself is solid. It's solid rock, right? And this is also for Mars the same thing. The mantle is solid rock, but the core, we think that the core on Mars is entirely liquid. And this has something to do with the size of the core, because having a very large core that is completely solid or partially solid, that would require a specific density, a specific temperature in the interior. And if you want to explain both the mass of the planet, the size of the core, and the temperature in the interior of the planet, you would need to have a liquid a liquid core inside Mars. I'm not sure if it's super easy to explain it, but it's kind of like, you know, it's a matter of mass, temperature, yeah, and the size of the core.
And says the core. And maybe we can give another hint in the terms of how the more deep we go, at least in the silicate material, this pressure raises the temperature, and then this whole thing melts at the base.
Exactly.
It is also another state of matter, right? That is favored there.
Exactly. And one could also imagine like the temperatures at which rock melt are different, are much higher compared to the temperatures at which metal melts, or metal-rich alloys melt. So therefore, for the core, most likely the temperatures, if the silicate are solid, for the core it's easier to get to have the core liquid for a longer time. And it always depends on how the planet has cooled during the thermal history, right? The stronger the cooling, the more efficient the cooling, the more likely it is to cool down as much as you could start to crystallize the metal. But other than that, you will have most likely a liquid layer.
So you could say that is also part of the remnant heat from the beginning of the formation of the planet that is trapped in there.
Exactly. Because this heat that is trapped in the interior of the planet, it only slowly goes, can be transported out of the planet, right? It's a matter of how well the material can conduct heat and can transport heat outside of the planet. And this is basically the thermal conductivity or the property of the rock. And this is more, it takes a longer time, it takes millions and billions of years to transport that heat out of the planet.
Nice. Thank you, Ina. Also, Elena, thanks you, and also Blairton for your answers. And I think we can also thank you for being with us today, and we can liberate you to go to your busy day.
Thank you very much for inviting me. It was really, really nice to see you all here. And yeah, I hope you enjoy the rest of the meeting.
Yes, if we have any more questions that are technical, I will forward them to you that I cannot answer.
Sure, absolutely.
Okay, thank you, Ina. Thank you. And now we can pass in the question of Ms. Maria Eleftheriou, who actually asks where we can find activities for students in order to speak for Mars, right? So that's what we will try to show here. I will share my screen. I want to actually talk to you for the Mars resources that are developed by Europlanet, which is the main topic we want to focus on today. So you already had an introduction by Ina about the planet's history and what we know And there are many more aspects of the planet that we can help the students understand better, and with it understand part of physics or even chemistry in a lot of times. We're gonna navigate together through the material that we have online, but first I can tell you a little bit of an overview, like what this material is aimed at, like which type of students, what ages. It's 10 to 14 years old. Of course, it depends on how advanced is your class, because you can introduce some concepts even earlier, especially with the help of videos that are supporting this. The second part is the languages. So we have these resources translated in 6 languages, plus a 7th. So we have English, which is accessible to most people, French, German, Greek, Russian, Spanish, and the whole package of resources has been translated in Italian by the Italian Astronomical Institute. So the resources are composed by 2 parts. Basically, there are the slides, which you can download either in PowerPoint form or in your PDF, whatever is better for you. And there is an accompanying teacher's guide for a 45-minute course for each of these presentations. You can follow it, and then it guides you through the discussion you can have with the students, what you want them to focus on, what questions you can make them think. And of course, if you don't have a lab at your classroom, we have provided recorded videos with experiments. They are no more than 1 or 2 minutes each. And you can see a real chemical experiment that is related to the material. So I have here a list of the modules, and we're going to see them also on the website, how you're going to access them. But the modules are 7 when it comes to Mars. The first one is the extremophiles, so life that can survive in extreme conditions. This can relate very well with the introduction to certain aspects of biology, like cell membranes, because a lot of these extremophiles live or are, let's put it this way, the extremophiles, we know them from the Earth, and those on Earth can survive on very salty places, which are very common in Mars, or they can survive in very high temperatures, and also in low temperatures, which, as we said, Mars is mostly the case. It is a cold planet today. This is, let's say, a starting point to talk about biology and cell membranes. The second is a brief history of Mars, which is touching upon the eras, the epochs that Ina already introduced. So it's geological history, and gives you a chance to talk also about climate change in another planet, of course, but climate change in geological terms. So we're talking about millions of years and not the recent climate change that we're experiencing, the human-made one. But it's a good topic to start the discussion. There are the volcanoes on Mars, which is much more particular to the volcanism. So again, relevant to geology, but also we introduce the concepts of convection of lava, for example. So fluid dynamics, a little bit how the warm fluid is setting into motion the body of the planet. This is another association. And of course, the rest, which are about 4 modules, the rest 4 modules have to do with chemistry. Chemistry in the sense of environment. So for example, you can start from, before you start from chemistry, you can start from more physical processes, such as the atmosphere, the atmospheric pressure and the temperature. Talk about sublimation of ice, that we have the different phases of the matter, and so on and so forth. So you can start from the physical processes, and then the rest of the topics, such as brines on Mars, so a lot of salts that we find on Mars, you can use them to introduce saturation of different solutions, crystallization, and also exothermic reactions. So you can make a nice introduction on different things. These are also supported by videos, by the way, experimental demonstrations. And there is also the evaporation and states of matter module, which is talking about how we lost the water, how we can have different phases of different material, and the states of matter again. And last is the pH of Mars. which is also another concept in chemistry that is introduced relatively late at school, but it depends on the country that you resided. So this is not a standard for every country. The curriculum varies. And the Mars collection of Europlanet is available online. So I am going to show you this. We can navigate together. Tell me if you can see my screen. I see something in the chat. Yes. So here is the Europlanet link. I'm gonna share it also in the chat for you so that you can also look at it in your free time. Thank you, Blairton, for confirming that we can see. So the Mars collection. As we said, everything is here in different languages. There are all these different slides, but you can find them also if you just go to the list, the comprehensive list that you find under the images. So we can start, I don't know which one would you like me to start with. We can start looking at some examples. For example, we can look at the extremophiles. And here, what you have is the presentations of the extremophiles. But I did say that this is accompanied by a teacher's guide. So the teacher's notes are exactly underneath in a different menu, and you can follow them with a PDF as well. Let's take a look at the presentations to see how they look like. There are not many slides each. We're looking at about 12 slides, 13 slides. So the extremophiles are going to be talking about life in extreme environments. We start with the objectives. For example, I'm going to show just this one example. You can explain the function of a cell membrane. We can introduce saying that the cells can change to adapt to extreme environments. And we can assess what are the stresses of Mars, on Mars. What are the environmental stresses for a life? What is the challenges it has to pass? Another discussion about what is an extreme environment. And then you can see examples of extreme environments on Earth, because we do have such environments on Earth. An introduction to the cell, pretty simplistic, but visually appealing, so that you can see the main components of the cell and the importance of the membrane in that case. And here we go, for example, to the video. Let me see if this is gonna play. Yes.
Cell with a semi-permeable membrane. Something large for our membrane, such as a pencil, will not be able to pass through that membrane to get into the cell. However, if we use something smaller that fits the shape of the semi-permeable membrane, such as a toothpick, it will easily pass through and into the cell. The cell membrane is one of the most important adaptations for single-celled organisms, which determine what sort of environments they can survive in.
So, for example, this was one minute video that introduces you to how the cell is a protective mechanism of the life inside. So let's go finish our example here. Here is some time for thought for the students. What might happen to cells under Mars-like conditions? And of course, you can combine these two different modules which are introducing the Mars-like conditions before, such like the history of Mars. There is another experiment demonstration with an egg membrane. I'm not going to show it to you, but it's available. And I think this is the example that has to do with the salt and the water. And you can see different effects. So actually, you can discuss further about habitability based on the results. At the end, you have a very short recap which is talking about the questions we addressed in the talk, in the course. What can cells do to adjust to an extreme environment? Why is the cell membrane important? And how do they cope with extreme conditions on Mars? That was one example, but you don't have to reinvent the wheel and think everything yourself, because as I said, the teacher's notes are accompanying every course. And in every teacher resource, we have a first table which says what you need to do this course. So a computer and a projector is actually the minimum that you need. And what are the learning outcomes? And every slide that you see here is accompanied by what you are encouraged to look into, so that you have a storytelling that is making sense by the end of the course. And of course, all the links to the videos are here. You see here like the semi-permeable membrane video, the egg membrane experiment. So, and you have also allocated time where you are supposed to interact with the students and ask them to give their opinion and think on the material. So in short, this is how the modules are structured. Let me see if we have any question. Please, at any point, you can interact me and ask me a question on anything you don't, you need clarifications. As I said, I see some question in the chat. Yes, thank you, Maria. So actually, what we have here is another unit after the teacher resources that is called Europlanet Planetary Field Analog Sites. This is actually something that is introducing places on Earth which we use to research phenomena on Mars, which is a very exciting thing to include in every lecture if it is relevant. And we have actually here which lecture is relevant to which place on Earth. And this is something that is helping to keep the imagination of the students active, right? So because they can also look forward to basically visiting these places maybe in their life once, or looking at what people look at there, because it's a very vivid, it's an exploratory activity, and we have explorers, modern explorers, that go to these places. And that's a very nice association to all the material on Mars. One is the Danakil Depression, that's in Ethiopia. The other is the Iceland field sites, which is volcanic. They are volcanic, but they also combine ice, so they're very particular places. Greenland as well has to do with the Martian chemistry module. And the Argentinian Ants, which is associated with the brines of Mars, and especially the salt, right? So we have a lot of salts that have been crystallizing on Mars, and we are looking at basically deserts, or if you want, shallow lakes that have that evaporate most of the time of the year, to investigate whether these lakes could have been viable, how they are on Earth, and how they could have been viable, like habitable for early Martian life. And there are salt pans as well. This one is in Botswana. Many places on Earth. The Rio Tinto, that is helping you in the topic of pH of Mars, especially when it comes to acidic environments. And of course, then you can combine with interviews of the EPSC. Give me a second. I need one very small break. We're back again. So you can make any question, anything that is more interesting you would like to focus on for these courses. I hope you all have the link and you can already start exploring it. So I mentioned some of the languages before, just to recapitulate on that. The extremophiles are the ones which are translated in the most languages. We're trying to keep up with all the other modules as well, but the Spanish is a little bit behind still. So far we have the Spanish language only for the extremophiles. And we have the Italian. You don't see them here because there is a whole separate website for the Italian supported by ENAF that you find at the top of the page, which is the EduINAF. That's the production organization, and they're available at Terra Chiama Marte. So this is a completely different website that has the same things, but is just on a separate server. Once you decide to use the resources and you see their effect on the classroom, like how they went, we also invite you to look at the survey menu so that you can give us feedback. Actually, we have it in many different languages, you see here, and it takes about 10 minutes, and it would help us a lot to improve and see what else we can add. So for example, I don't know if in your curriculum already at the ages that you are teaching, these topics that we said are already addressed. So for example, let's go a little bit here. I would like to ask you if you have arrived at the point where you start teaching some introduction to chemistry, and if yes, which part it is? It would help us understand a lot. You can always unmute your microphone and speak, or I can read your answers in the chat. Because, for example, most of these resources are for 10, 14 years old students. Are you teaching older students or younger? Okay, I see here from Greece that we have biology about the cell in 12 to 18. So you start a bit later, but it's still, I think, within the range of ages. Okay, interesting. I don't know which other countries you're joining us from. Maybe you can also say. You can write on the chat to know how international we are today. So the biology is a little bit later. The chemistry, I'm wondering if it's also later. Okay, I see in Kosovo, students learn astronomy at grade 12. Is grade 12 not age 12, right? This is at 18 years old, if I'm not wrong. Just to make sure, because don't want to misunderstand anything. Yes, thank you, Blerton. So astronomy, actually, the astronomy is a topic that almost all of these modules touch upon, maybe more the brief history of Mars and the volcanoes of Mars, because a lot of those we are actually observing thanks to satellites. We need global data, and that's planetary missions. So that's an extension of astronomy, how we do astronomy from close by to planets. But we also can see some features, some aspects of the atmosphere of Mars, for example, already from spectroscopy that we can do from Earth. Of course, the resolution is much better, and we can see the weather better and predict it even on Mars, thanks to the orbiters. But yes, thank you, Blerton. I see also that chemistry, and geology are taught, like for volcanoes, around 12 to 13 in Greece, and pH, acid basic solutions, 13 to 15. So that's already yeah, towards the end of the target group that we have, but still including. And you know, the volcanoes on Mars are of different types, so you can talk about different procedures, and it's very interesting because we have so many different volcanoes on Mars. We also have the biggest, the tallest, excuse me, mountain on the solar system, found until now. So about 20 kilometers, the Olympus Mons. So that's actually very nice. For the climate change, yes, we don't teach it. You don't teach it, I say. It's something that is anyways discussed everywhere outside the classroom, I guess. Yeah, it could be complemented. It could be complemented by talking about climate change in Mars, like geological climate change. So yes, this could be one more, let's say, starting point to talk about climate change there. But thank you for the input, Maria. Okay, I see we have a couple of more minutes. If there are more questions, I'm here to take them. Let me know if you would like the slides, basically the one of the curriculum topics, because the rest are all found in the online. But it's a short overview that I made to have a better and quick overview of what are the resources about. So if you would like them, I can send them to you. Yes, I see we don't have many more questions. Feel free to contact me also after if you come up with any more questions. And if you happen to use the resources, we would appreciate your feedback with the survey. And any time you can devote to that. So thank you everyone. Thank you for being here, and looking forward to see you possibly in another session, or if you already attend some of the lectures of the rest of the week, also in some of them. So have a nice afternoon, everyone, and good start of the school year.